Hello, good morning, everyone. Can somebody confirm if you can hear me clearly? Is everyone hearing me clearly? I need someone to confirm if you can hear me clearly.
Yeah, I
Thank
can
you
hear.
so much. Thank you for confirming that. I want to welcome you into my lecture today. Of course, we're having this lecture remotely because of little emergency that I have. That's already clearing out. So, we started this topic earlier in the week, called discrimination and classification. Before I go into the topic, I'm gonna say this. I did not post a new assignment this week just because of the makeup I'm actually going to post tonight. I said I was going to give another opportunity, to those who are interested in the makeup that will be posted. So I decided not to post assignment because I want you to get yourself familiarized with the solutions, midterm two solution that I posted. So, watch out tonight. I'm actually gonna post the makeup too with some instruction. I'm actually gonna send instructions, through the announcement section before the time. So you're gonna have like 48 hours, to you can start at any time within the 48 hours, but the exam is being programmed for just 1 hour. Okay, so I'm actually earlier in the week, like I said, I started discrimination and classification. So we've been able to achieve the first two objective, which is classifying two populations and two multivariate normals. Okay, and I think we also touched some parts of evaluating classification. So, what is going to take center stage today is how do we actually, you know, classify more than two populations? I mean, how do we classify observations into more than two groups instead of two groups that we've been actually talking about? Then there's going to be, a practical illustration of this technique on the well-known iris data. Okay, so I'm actually gonna quickly move all the way to where we stopped in the last class. Okay, so I think I mentioned in the last class, let me start from here because of the fact that the one that I walked you through the other time, we were classifying, we are assuming that the population covariance structure of the two classes are the same. But what if in a situation where they are not the same? That's what you're seeing here. So where they are not the same, the technique becomes what I call quadratic or discriminant analysis. I'm going to say that again. So where the covariance structure are the same is, we call the technique linear discriminant analysis. But where the covariance structure are not the same, we call that quadratic discriminant analysis. So right now, this is a multivariate distribution, based on a K class. And of course, because we're considering two groups, so K quarter one and two, take a look at that, group one and group two. So when I plug in wherever I see K here, I plug in one. Okay, that's going to be F of one S. When I plug in two, wherever I see K, that'll be F of two. So when I do the ratio of that, I'm actually going to get this out. Take a look at that. Take a look at what I'm going to get out. When you take a look at what I have here, you're actually going to see the covariance structure for the first group, the covariance structure for the second group. So it's actually part of this. This is different from what we saw when the covariance structure are the same. Okay? So that is the F star. And of course, the way we're going to choose the F star, we're going to choose the F star in a way, I mean, the F star will enable us to choose, to be able to classify our observations into different region, whether region one or region two. So if we want to do that, don't forget, I said the other time, the regions will minimize the expected cost of misclassification. That's what I call ECM. So if the logarithm of this guy here, F star is the whole of that guy, right? And if I ask you to show this in exam, how do we derive this? It's just plugging in wherever you see K here, plug in 1, get F of FF1S. Wherever you see K, plug in 2, you get F of 2S. Then you do the ratio. Mathematically, speaking, after algebraic or simplification, this is what you're going to have as your F star. Now, when you have this as your F star, then we're going to take the log. Okay, so taking the log, then we're going to compare. You can see what I'm doing here. When the log of that is greater or equal to the log of this, don't forget, I told you the other time what this represents. The first one is the cost of misclassification. Okay, you classify objects into group one and it's supposed to be in group two. And the other one, you classify objects into group two, supposed to be group one. And of course, these are the P1 and the P2 are the prior probability, the prior probability. So this is the condition now to actually allocate. Okay, so now in practice, you may actually like, okay, you have data set, you have data set. So how are you gonna figure out? Because you need to figure out all of this, before you can compare, with this. So how are you going to achieve that, when you're given data set? And of course, it means the meal one, the meal two, you're actually going to use their estimates. Okay, the estimate is going to be x bar one and x bar two. And of course, the sigma one, the sigma two that I call population covariance structure, you're actually going to use their sample estimates. Okay, so which is what I'm trying to talk about here. Like all these parameters, they're actually unknown in practice, though they need to be estimated. That's exactly what you're seeing here. You can see now the meal one is estimated using the sample mean, the meal two using the sample mean. And also that, we are estimating the covariance structure for the first group and for the second group. Okay, so now, and at the end of the day, you know, the estimated, you can see a cap on that, right? The estimated half is going to be this guy here. You can see, this is sample estimate version of what we have, of what we have here. Okay, what you have here is a population version. Okay, this is a population version. We are the mu one, the mu two, the sigma one, the sigma two, they are all population parameters. Okay, but after estimating them, this is what we're actually gonna have after estimating them. Okay, and this is gonna be called estimated classification rule. Okay, because what if I ask you that in exam, that you should state the estimated classification rule, for situation where the two groups, do not have the same covariance structure. Okay. Can somebody confirm again if you are still hearing me clearly? Is everyone still hearing me clearly?
Yes.
Yes.
Thank you so much. Thank you for confirming that. In case you have question, one or two question, I'm actually taking this as a regular class, where you can where you can ask your question. Okay, now we are still on the on that. So mathematically speaking, if if I have the F estimate of the F, just like what we did in the population aspect, we're gonna find the log, right? We're gonna find the logarithm of that. We also so we want to find the logarithm now. That's what you see here. So finding the logarithm. So I'm gonna have the log of all of that. Take a look at that. Now, do you know this expression can actually be simplified into y cap minus m cap? So we are um the y cap is actually going to be this. This is after we have simplified algebraically. Okay, this after we've simplified algebraically. Okay, so you can try that, trying to take the log. Okay, and the log, the log of all of that is going to be the log of this guy. And the log of this guy is just going to be minus half log of this, which is so minus half, which is what you're having here. Okay, why is the minus disappearing here? Because we say minus m. Okay, minus m. So when I say minus m, of course, you're going to see the minus here for all of this. Okay, so take a look at that. And when you take the log of the exponential, right? Because the log we're taking is a natural log, the exponential is going to disappear. Okay, then after simplifying all of that, so that's what you're going to have. So what we're trying to tell the world right now, okay, the log of the estimate of the function can be written as just this, where this guy is that and that guy is that. And of course, we can go back to so like I said, the y cap, okay, when you take a look at if you take a look at this one now, that's quadratic in nature. Oh my God. How do I know it's going to be quadratic? I need you to pay attention to this. You remember, that's looking like a quadratic form, right? Remember quadratic form? Okay, where we have this guy. You remember? That's a quadratic form, right? So, and that is why situation or where the two groups are not having the same covariance. Okay, we're going to call that discriminant, a classification technique, quadratic or discriminant analysis. So take a look at that. So our A now, A is when you take a look at what you're seeing here, so it's actually looking so this is my A. That's looking like my A now. Take a look at that. That's my A, right? So take a look at that. So this is a quadratic, discriminant analysis. Don't forget, I told you what leads us to quadratic discriminant analysis is when the two covariant structure are not the same. But if the two covariant structure are the same, then that would be linear discriminant analysis. I just wanted to take note of that. So that's what I'm trying to say here. Now, can we have here I say caution, quadratic classification of a non-normal data. Now I need you to pay attention because we are hiding under the assumptions of normality. Okay, you need to be very, very careful. If the assumptions of normality fail, we may not be able to use this approach. Okay, now when you take a look at this, the shape right now, take a look at that right now. You're actually gonna see where the two of them are two normal. This is normal curve. These are normal curve. The way they spread out may be different. You can see here the variance of this one is different from the variance of that one. One is more spread out, the F1. Okay, F1 is more spread out, while the F2 is shrinking. So, which is telling you we do not have the same covariance structure, but the fact that despite the fact that we do not have the same covariance structure, the two of them still follow normal distribution. But I want you to take a look at the second one. Oh my God. Look at the second one. It's looking as if it's only the F2S that follow normal distribution. If you look at the F1 of S, that does not follow normal distribution. And because of that, the our rule of classification is not going to hold anymore. So before you can actually, perform a classification technique, you know, because we assume assumptions of normality, you got to make sure that the population has a no, it's a normal population. Otherwise, it's not going to be appropriate. The approach is not going to be appropriate because we hide under the assumptions of normality. So I need you to pay attention to the two. Okay, the one we can actually apply our classification rule is this guy here. When you take a look at this guy, the two function follow the two core follow normal distribution, even though they don't spread out the same way. It doesn't matter. They don't spread out the same way. Is the reason why we call that quadratic classification, because what is going to lead to quadratic classification is actually when the covariance or structure of the two classes are not the same. So, but if you take a look at the second one, that's a violations of normality to the density function of the first class. You can see the first class, you can see the way this shape doesn't look like a normality. But when you take a look at the shape of the F2, that is normal. So the fact that a normality assumptions have been violated in the second one, using moving forward, using classification rule that rely on the assumptions of normality will mislead the world. That's what I'm saying. Okay, now I'm actually gonna move. Now, how do we evaluate classification functions? Evaluating classification function is more or less like, how am I going to know my classification technique has done a great job? And why do I need to investigate this? Because we live in a world where we're trying to depict reality. We want to speak the mind of the nature, and the best model ever, okay, is never going to give an exact characterization of reality. Okay, we acknowledge that fact in statistics that there's going to be a gap between reality and what the model suggests, and that is the reason, because of the existence of error, because there's going to be an error due to misclassification. So we can actually have a way to evaluate the performance of our classifier. Okay, and that's going to take us into, is there a way we can quantify the quality of a classification rule? Quantify the quality of a classification rule is actually to determine whether the rule that you have applied is good. So what we can do in that regard is we can examine the error rates. Okay. Now, how do we examine the error rate? Is you'll find in what I call the probability of misclassification. Okay, the probability of misclassification. So we got a technique, to estimate, the error rate from the observed data. Okay, so in case our intention is actually, you know, we want to before we go ahead, classifying new data. Okay, we are actually going to consider some cross-validation procedure. Now, so which means we need to follow first, if you want to calculate the probability of misclassification, we need to follow first like recognize the possible classification probability that exists. I remember the other time I gave you the two type of misclassification. One where maybe an object is supposed to be in class 2. You classify the object into class 1. Okay. Now the error associated with that. What about if an object is supposed to be in class 1 and that is classified to be class 2? So what you are saying here is actually the total. Okay, the total probability of misclassification. You can take a look at that now. Okay, that's what we are adding now. And you can see that each of these integra, is multiplied by P1 and P2, which are the prior probability. Okay, so take a look at that. Now, from there, we can actually find what I call the optimum error rate, OER. So the optimal error rate is actually the minimum possible value, the minimum possible value of this guy. Okay, the minimum. We want to minimize that. The minimum possible value of the total probability of misclassification. That's what I'm talking about. Okay. And that is the reason why I said, want to minimize, okay, the error due to misclassification for the total probability of misclassification. And that will be subject to the, you know, the omega, I tell the omega the other time I talk about the possibility, you have the regions, combining the region together. And of course, if you want to obtain that, we've actually use a threshold that if the ratio of the normal density for the first one, the second population is greater or equal to the ratio of the priors. Take a look at that. That's for group one, and this guy for group two. But you know what? We're only going to consider ratio of prior probability in a situation where we deem the classification cost to be the same for the two. Don't forget we got two different form of classification calls in a situation where they are the same. Of course, there's going to be the threshold, the classification rule. Okay, now we also have, apart from the OER that I call the optimum error rate, you can also figure out the actual error rate. Okay, now the actual error rate. Okay, so we can figure it out. If you are using the ADA, for instance, don't forget what do I mean by ADA. The ADA is linear discriminant analysis. We use linear discriminant analysis when the covariance structure of the two classes we want to compare is assumed to be the same. And that is why you see this guy here. We used to just be, the equality. You can see I did not say sigma 1, sigma 2, because we are assuming that the two classes have the same covariance structure. The only difference is just the difference of means, but the same covariance structure. So that is for the ADA. But when I want to talk about QDA, that I call linear discriminant, sorry, that I call quadratic discriminant analysis, okay, you're actually going to have different covariance structure in that regard. But right now, the same covariance structure. Now, how do we find error rate and the actual error rate? Okay, how do we actually obtain that? Of course, we're gonna obtain that from the sample. That's why you see a cap on that. So you can see this now. Putting a cap on R2, keep putting a cap on R1. This is it. This is still gonna tell us the total misclassification probability, but this is an estimated one. It's an estimated one. The estimated one is actually the actual error rate that we found using the sample estimates. And of course, the arrow cap one, the arrow cap two denote the estimate from the sample sizes N1 and N2. Okay, now I want to walk you through a cross tabulation table, that will make it so easy for you to determine what I call the apparent error rate. But before moving forward, I need somebody to confirm again if you are still hearing me clearly. Is everyone still hearing me clearly?
Yes.
Thank you so much. Thank you for confirming that. Like I said, if you need some kind of clarification, I need you to ask me question. Is there any question moving forward from anyone? Is there any question? I need you to ask me a question in case you have any question for me. Okay. Now, the absence implies you really understand what I'm talking about. Now, right now, I want to walk you through the parallel array. Okay, so I'm going to use what I call conversion matrix, but this is the way we do it. This is the way we do it. Okay, we actually going to split our data set. Okay, because the only way we're going to know whether our model is going to do a great job. Okay, when we want to classify object into group or we want to make prediction is for us to be able to is trying to split our data set. We're going to have a training one, we're going to have a test one. Okay, now on the training, I said, yeah, estimate the AER using the observe. Okay, we know the training sample of data is what I talk about. Now, this is going to be the confusion matrix associated. Now, in this confusion matrix, I really want you to see what I'm showcasing now as you know, um, the type one and type two error in the lower level statistics, where there's possibility of rejecting an hypothesis and rejecting it not when it is true and failure to reject that when it is false. So which we call, the type one and the type two error. And of course, you're also going to have situation whereby you take a correct decision, when the non-hypothesis is true. It's true, you don't reject it. When the non-hypothesis is false, you reject that. That's going to be a correct decision. If you take a look at this, when I say truth, this is what nature knows. Nature always know the truth. But this is our action because most of the time we want to speak the mind of nature. But let me tell you this, at times we speak the mind of the nature correctly. At times we do. We don't speak the mind of the nature correctly. Okay. Now there's something I need you to pay attention to now. Okay, now I need you to take a look at this diagonal one. Take a look at this. Oh my God. By nature, okay, by nature, because nature knows the truth, that observation is supposed to be in group one, and you classify the observation into group one. Okay, the NC1 now, okay, will be the number of correctly classified observation into group one. Now, this one is okay. The observation is supposed to be in group two, and you correctly classify the observation into group two. Now, the NC2 now is the number of correctly specified in that group two. Okay, so which means that the right diagonal in the confusion matrix right now, is represent the number correctly classified. Maybe you want to talk about emails. We normally receive a lot of emails. At times you got spam and some are not spam. Okay, so what we're trying to say here, you receive an email that is not a spam by nature, and you classify that email as a good one. And you receive an email that is a spam, and you classify that as a spam. So which means you've taken correct decision. But you know what? Another thing exists in the world where we don't get it right. We don't get things right. Oh my God. We don't get it right. The nature says it should be the object should be in group one, but your model classify the object to be in group two. Okay, the NM1, okay, represent that. And the same thing with the NM2. So I just wanted to take note of that. So what I'm trying to explain right here now, okay, if this is the total, okay, if this is the total, if I have this guy, okay, and if I subtract this guy from the total, that's going to give me this guy. This is what I'm trying to say here. Okay, the same thing applicable here. This is the total, right? That is a total. Okay, the total of what? This is a total, by nature that should be the observation that should be in group two. This is the total by nature, the observation that should be in group one. Okay, so right now you are able to find the probability of misclassification. So what the confusion matrix is going to give, the confusion matrix is going to reveal to us, the numbers that were correctly classified and the number that were misclassified. Okay, now this continue. Okay, now that we have gotten this out, do you know we can now get the APE out? Don't forget. So talk about APE out, the apparent error rate. Okay, the apparent error rate. Okay, now from the confusion matrix now. Okay, if I'm, because I'm interested in the totality, okay, the totality of the mistakes. Okay, that is the totality. Then I'm adding them up, right? Divided by the totality. Okay, divided by that. Can you see that? So which is going to give you what I call the total proportion of misclassified sample observations. And don't forget, well, our intention is to minimize that kind of error. We want to minimize it. Okay. Now we have an approach in case you want to estimate this guy here, right? We get an approach that we use. Okay. Approach of cross validation. Okay, the approach of cross validation is leave one out. One of them is leave one out. Okay, leave one out where you actually use all the observation in one group. I mean, you use nearly all the observation in one group. You leave one out. Okay, probably to be able to predict that to see whether your model is going to do a great job. You already know what the group is that belong. That's what I'm trying to say here. Okay, population one, I say hold out the height observation from group one. Okay, when you are building, when you want to build your classification rule, okay, you are not going to use all the observations in the group one. You leave one out. That one that you leave out is what you're now going to test your model on. You're going to build your model on the one that you include, except one. And after you've built your classification rule, then you're going to use your classification rule to classify the one that you did not, the one that you leave out. Don't forget, you already know the group it belongs. You know it's in group one. You intentionally leave it out. Okay, you want to assess the performance of your model. If your model is going to do a great job, it should be able to predict that to be in group one. You do the same thing to group two. Okay, you leave an observation out when building your classification rule, and you use a classification rule to classify the observation you leave out. That's what I mean there. And of course, you know, like and this is an estimate, the unbiased estimate of the expected, the AER. Okay, and of course, don't forget here, this guy here now will be the number of misclassified observation using the procedure that I just mentioned, the leave out procedure. Okay, before moving forward, is there any question? Is there any question before moving forward? We're actually going to do this 3 times. This is the second time we're working on this. So we're still gonna work on this 3 times. So wherever we stop is where we're gonna continue. We don't want to rush. Okay, don't want to rush you at all. Now, I want to also revisit linear discriminant analysis. Don't forget, in the linear discriminant analysis, the covariance structure are the same for the two population. You can see the only difference is just the mean. Okay, now we want to revisit that now. Okay, and don't forget, I told you the other time, we could have a situation where the cause of misclassification is the same for two groups. And of course, the prior probability the same in that regard. Then you're actually going to have one, right? So you're going to be comparing the ratio of the density of the two, density with one. Okay. Now, in that regard, don't forget the classification rule is actually going to be why? So for this scenario now, okay, Because in exam, what if I actually say, okay, you want to use a linear discriminant analysis in a situation where the cost of classification, the two possible costs of classification is the same, and the prior probability of the two groups are the same. So if I mention that, then this is going to be your classification rule. Okay, I'm actually gonna say, I'm gonna classify object into group one, okay, if y is greater than or equal to m. And I'm gonna classify object into group two, okay, if y is less than m. And what is the m? What is y? What is my y? What is m? So for this classification rule, where this happen, okay, my y is gonna be that, and my m is gonna be that. If you take a look at my hem right now, my hem is the midpoint of the two means, right? The midpoint of the two means, right? And my y is actually a prime s. So what is a prime? Okay, what is a prime? Oh, this is a prime. That's my a prime. The A prime is a function of of the means, and the inverse. You can say the inverse of the covariance. Take a look at that. And of course, you may be wondering, how am I going to get this guy? Oh my God, it is that guy. Okay, please pay attention. There's a lot of calculation here. Okay, in each of that. Okay, if I want to get, before I can get M, I need to first get this guy and this guy. And this is the way to get this guy. Can you see them? And you know the mu1 and mu2, right? Mu y1 is different from mu1. The mu y1 is a prime multiplied by mu1. Okay, what is a prime? Oh my God, this is a prime. This is how you're going to set up your A. It is the same A prime that you're actually going to use here. Is there anyone who doesn't understand this, any of this? Please pay attention. The midpoint that I'm talking about here, okay, is the midpoint of the this and this, not the midpoint of mu1 and mu2. There's a difference between mu1 and mu2 and mu y1 and mu y2. Okay, the mu y1, you can get that as a linear combination of mu1. And what is your a prime? This is your a prime. Take a look at that. What is your mu2? That's a prime mu2. Take a look at that. Okay. Can somebody confirm again? If everyone's still hearing me clearly, is everyone still hearing me clearly?
Yes.
Thank you so much. Thank you for confirming that. Now I'm bringing it out right now. Okay. And please, I need everyone to pay attention. Where we are now is very crucial. So y equal to that, like I said, and I can rewrite that as this because of this fact that my a prime is actually mu1 minus mu2 prime, or the inverse of sigma. Okay. Now this is my mu y1. This is my mu y2. This is the variance now. Now, I need you to pay attention. You remember earlier in the semester when you want to talk about the variance of a linear combination? You remember this guy, right? Okay, that is A prime. Okay, the variance covariance A. And in this case, okay, what is my A prime? Okay, my A prime, please pay attention. My A prime is this guy. That's my A prime, right? Okay. So if I write the A prime out, okay, so this guy is A prime, right? Okay. I got A prime, okay? And I write this guy and I write A, okay? At the end of the day, when I simplify that, this is what I'm gonna have. This is what I'm gonna have, okay? Now this, for the variance of Y, I can use this notation, okay? Delta squared, to represent that. So whenever you say a delta squared, I'm referring to the variance of y, which is also having this as an expression. Please pay attention to that. Okay? Pay attention to that. Okay? Because we have a linear combination right now. And in the linear combination, okay, we have the mean for y1, we have the mean for y2, we have the covariance, okay, structure, which is expressed as that. Just pay attention. Pay attention. Now, do you know I'm actually going to say, okay, now my linear combination y follow normal distribution. Don't forget, because I have two classes. For the first class, this is the mean. Don't forget, the mean here, the mean y1, the whole of this guy. Okay, the mean y2, the whole of this guy. They're both going to have the same variances, delta squared. That's why I say delta squared, delta squared. So the delta squared is the whole of this. They have the same common variances. Don't forget, I'm talking about, linear discriminant analysis. Okay, now visualizing the misclassification in ADA now, please, I need you to pay attention. Okay, you know, when you take a look at the density for group two, it go from stretch from there to there. The one for group one stretch from here to here. And you can see the mean for the second one, the mean for the first one, but they both have the same covariance structure. Take a look at that. But you know what? Because they overlap, right? Because they overlap, there's possibility of misclassification probability. Now, if you take a look at this P2 given one, okay, it was classified to be in group two, supposed to be in group one. And you see this guy, it was classified to be in group one, but supposed to be in group two. Now, can we have a way to measure? Please pay attention. Whenever a misclassification is made, whenever a misclassification is made, it's going to tell on the variance. I'm going to say that again. Whenever a misclassification occurs, it's going to tell on the variance. And that is the reason why here, when you look at the measure of that space, okay, is in terms of the variance delta squared. You see, that's delta squared over 2, and that one delta squared over 2. Pay attention to that. Where the delta squared. Okay, can you see that now? Okay. And you know what? Since the covariance structure are the same, then our assumption here is that, okay, the length of the misclassification also going to be the same because everything here is delta squared. But they're going to share that. That's why you see delta squared over 2 for that, delta squared over 2 for that. They're going to share that. Okay? So that's what I mean. Now, how do we put this into, how do we calculate? Now I need you to pay attention. How do I calculate misclassification probability in ADA? Then, if you want to do that, because of the fact that we're working with normal distribution, I'm going to say that again. Because we are working with normal distribution, this will be very easy to compute because normality facilitates standardization. I'm going to say that again. Normality facilitates standardization. It means I will be able to use z-score. I'll be able to use z-score because ADA operate under the assumptions of normality. Okay, so what I'm gonna do now, I want to find, don't forget, I want to find the probability associated with misclassification. Now, I want to find right now the probability I misclassify pi 1 as pi 2. Okay, I misclassify pi 1 as pi 2, something that's supposed to be classified as a group in group 1, but I classify that as in group 2. And don't forget, what I'm going to find is the probability of y less than m. Oh my God, where is the y less than m coming from? Oh, it's right here. Take a look at that. Because I'm classifying that into group 2. Okay, y less than m is supposed to be in group 1, where y greater or equal to m. But I classify that into group 2. So I'm going to find the probability associated with y less than m. So if I wanted to do that, the probability of y less than m, then you know what I'm doing here. Please pay attention. What I'm doing here right now, I'm actually using a z-score. Do you remember a Z-score that we've done in this class? Don't forget normality, facilitate, standardization, and of course, the standardization facilitate the use of z-score. So right now I'm going to do y minus the mean of that divided by that. Okay, now if I'm going to do that, okay, my y is my m. Then the mean, you remember the mean that I talked about before. Okay, this is the mean. Do you see that mean? The mean of for group, the mean of the linear combination of the first group. And what did I call the sigma squared y? Oh my God. The sigma squared y. I refer to that as a delta squared, but in a z-score, the denominator is the standard deviation, and that's why you see I'm finding the square root. The square root of a delta square is going to be delta. Take a look at that. Okay, now the next thing that I also want to show you now is that the whole of this guy that you're actually seeing here now, okay, is the same. The numerator here is something as minus half delta squared. And what you're going to check for at the end of the day is just going to be this guy from a table. Like for instance, here you're going to do a p norm. You're going to do p norm if you want to check that out. What is a p norm of a negative delta, okay, divided by 2? What is a p norm? That's what you're going to check for to be able to know that probability of misclassification. I think somebody texted me on. Somebody said, let me see. I have a question about makeup midtime. Does it only cover material from midterm two, not from, yeah, the makeup is for midterm two, not for midterm one. So it's only going to cover the materials, the area that I told you the midterm two cover, the same area midterm two cover. That is what I think I'm going to say something about that when I'm done. Okay, so that will give you opportunity. So don't forget, which means what is my data? Data is what you're going to be looking for. I'm going to show you. You know data squared, right? It will know data is going to be easy. So data squared. This is data squared. Can you see data squared? I'm only going to find the square roots. Look at that. This is data squared. Okay. What is the square root of of that? That's going to be just data. You hear me? It's going to be data. Okay. It's going to be data. When I find square root, that's exactly what you're seeing now. We're using data here. Okay, we're using data here. Take a look at that. Now, the same way we can also calculate the probability of classifying, pi 2 as pi 1. You know what I used the other time. I use y less than m. I'm going to use y greater or equal to m, and I'm going to proceed the same way. And this is obvious. It's going to be so in R. This guy is going to be 1 minus p norm of that. Okay, then you'll be able to figure it out. Uh, I think what I'm going to do, I'm going to start from, like I said, we're meeting 3 times. The second time on this material, the third time will be on Monday. Okay, so this way I'm actually, it's very, very interesting. So we're going to finish this material on Monday. But you know what? Is there any question before I go? Like I said, I'm actually going to post a makeup exam today, okay, to this night, and it's going to be left on for 48 hours, 2 days. You can start at any time. The moment they are all going to be multiple choice, okay, that you can finish in 1 hour. Okay, so get your calculator. uh you know you can actually um you know check you can check your math. You can It's an open book, but you cannot search online. You can't search for anything online. In fact, you're going to waste your time when you search things online. Okay, so it's an open book exam. But when you want to write the exam, whenever you want to write the exam, you log on to the Zoom. You log out to the Zoom with your video on. Even though I'm not going to be on the Zoom, it's going to be recording you. And the moment you are done with your exam, you're going to receive your score automatically. And what I'm going to do at the end of the day, I'm going to use the higher score. I will compare your makeup score with your midterm to score, the one I'm going to use at the end of the day will be the higher one. So
Wait,
yeah,
excuse me, I got a quick question.
go ahead.
So is the this makeup, will it cover midterm one material or midterm two material or like both?
Only midterm two material. This is a makeup for midterm two, not for midterm one. So
Oh, okay.
only the area that was covered in the midterm two.
Okay.
Uh, Have I answered your question?
Yeah.
Okay. Is there any other question before I go today?
So we'll be able to use our markdown to be able to answer the questions as well,
Yeah.
right? Okay.
Yeah. So you can use anything that will make you to succeed, except that you cannot search for
And
any
then
clue online.
we will, it's a multiple choice exam, or do we fill in the answer?
It's a multiple choice exam where
And
I
then
only, okay, go ahead.
oh, so we'll just have to, it's like a Canvas quiz. We open it
Yeah.
up, we
Mm-hmm.
choose the answers after we
Mm-hmm.
find the answers, and we can refer to our notes. And then do you need us to turn in our work after we're done, or just the
No,
work? Okay.
no. You don't need to turn in anything. So I only want to see the correct option. And the way I've done it, I know students are going to do this exam at different time. So the exam is randomized. The number one question in your exam is going to be different from number one question in another person exam. So that is it. And whenever I'm going to provide a Zoom link, there's going to be a Zoom link as part of the instruction that you're going to click on because I want to see the person writing the exam. And if you're
And
on
then
the Zoom, okay, go ahead.
I apologize. When do you anticipate that you'll be opening that today?
Okay, because it's going to be left open for 48 hours, targeting uh, by 11:15, before 11:59 p.m. today, because I'm going to leave it open for 48 hours, 11:59 p.m. on Sunday. So I'm going to open that before 11:59 p.m. today.
Oh, so really we're not meant to start today. It's more tomorrow.
Exactly. So even you may not do it tomorrow if you don't want, you may can do it on Sunday because it's going to be left open for 48 hours. So if you want to, for those of you who want to, if you want to start like 10:59, let's say for instance you decide to start by 10 p.m. on Sunday night, of course you can still start at 10 p.m. on Sunday night because the last time the exam is going to be visible on Canvas is 11:59 p.m. on Sunday night. Okay, so
Professor, for those of
okay.
us, I do appreciate the 48 hours, by the way. I really do. Um, I was really hoping to take that today. Is there any way we could st open it a little earlier, just to give us a chance to get started on it?
Uh, or you mean like for those of you who want to start today, right?
Yeah.
Okay, this is what I'm going to do. Uh, if I can do that, I can do like 6 p.m. What about 6 p.m.?
Yeah, that'd be great.
Okay, so if it's gonna be 6 p.m., okay, so I think by 6 p.m. for those who want to start today, that's no problem. So I'm gonna program that you're gonna have the access by 6 p.m.
Great.
Okay, so is there any other question before I go?
There's some questions in the chat.
Oh, a question in the chat. Okay, then I'm gonna check. Okay, does it only cover? Okay, I think I've answered it. That is just going to be midterm two. Somebody said, is the Zoom link? Yeah, the Zoom link is the same link for class, but I'm still going to share that as well. It's the same Zoom link that we're using in this class. The one we use right today, the same as the one we're using now, but I'm still going to put that as part of instruction. Somebody said, I still have a question. So if we have midterm two on Friday, when can we make up midterm one? Okay, you know what? The same way I'm going to conduct midterm two, it's the same way I'm going to conduct midterm one. So, for the midterm one, that would be next week, not this week. So the same way that I did, like, okay, Friday to whatever, I'm also gonna do that for midterm one as well. But I want to for first time midterm two first. Okay? So somebody said is a rear of the last and the retake midterm 1678. Oh, okay. Okay. Now, thank you for reminding me that I've changed my mind. So it's not gonna be 70-30 anymore. So I'm gonna use the higher score. Okay? I don't know if I've answered the person question. It's gonna be higher score. Okay? It's gonna be higher score because I, my intention is to make what can I do? I always think of what I'm gonna do, to make our student improve on their grade. I believe in second chance, so that's why I've been doing what I'm doing. So now I wanted to make use of the opportunity of the second chance. And that's why I release, the midterm question, the midterm solution, so that you're gonna get yourself familiarized with that, so that you're gonna be in the best position to write the makeup. Okay, because I want a situation the moment you submit, you're actually gonna see your result immediately you submit, immediately, because it has been programmed. Get ready with your calculator. Get ready with anything that will make you to succeed. Get ready with your notes. It's an open note, okay? But the only thing you cannot do in the makeup, you cannot search for clue online. You're going to be wasting your time searching for clue. You can't do that. And you cannot, seek assistance from your colleague or provide assistance. You can't do that, okay? So I wish you, everyone, best of luck. See you on Monday in class. Okay, bye for now, everyone.
Hey, thank you. Can I ask you one more question before you go?
Oh, go ahead. Go ahead. Go
This is
ahead.
about the project. The syllabus has some information on the project, but you also gave a lot of information in class. And so my group has the project area that we're focused on. In my case, it's multivariate normal. And so we're going to be doing a multivariate normal data analysis on the data. Um, do you expect us to do other techniques as well on the data?
Yeah, that's it. Thank you for asking that question. So, You know, what I only want is, okay, since your group is working on motivated normal, so what you need to prioritize is, okay, how do we investigate data set for normality in the first place? Okay, so if I have one variable, okay, that how do I test data set for no, univariate normality? If I have several variables, how do I test data for multivariate normality? So then we also expect that you make mention of the plot that they use. What kind of plot did they use? How did they take decision using the plot? And if there is any other statistical tests, that they can